Welcome back to the deep dive. Today we are strapping in for a ride into the universe's most constant yet least understood phenomena, gravity.
It's everywhere.
It's everywhere. You feel it every second of every day. But I promise you, when we finish this deep dive, your entire mental model of what gravity is will be fundamentally broken and rebuilt.
I think that's a guarantee.
The hook. It's absolutely not what you think it is.
That's right. I mean, if you are operating on that, 17th century idea that gravity is a simple, invisible force pulling objects together,
Yeah.
Isaac Newton's view, then, yeah, prepare for a massive intellectual overhaul.
It's time to upgrade the software.
Definitely. The sources we've gathered today, including historical letters and some really cutting-edge theoretical physics, they just challenge that traditional notion completely. They suggest gravity is either purely geometry or, and this is the wild one, perhaps a deep thermodynamic illusion.
Driven by information and heat. Sounds like science fiction.
It really does.
Okay, so let's unpack this and set our course. Our mission today is to give you a shortcut to understanding three monumental, mind-bending concepts that redefine reality. First, we'll analyze how Albert Einstein basically killed the idea of gravity as a force and replaced it with the idea of curved space and time.
That's General Relativity, or GR, the first big revolution.
Right. Second, we're diving into the truly radical stuff, the 21st century front lines of physics, a controversial modern theory called entropic gravity.
And this framework suggests gravity is not fundamental at all, but an emergent phenomenon, like a cosmic echo of the universe trying to, well, maximize disorder.
And finally, we'll dive deep into the human element of discovery, the painful 3-year intellectual struggle Einstein endured to find the final, correct mathematical description of his revolutionary idea.
It's a powerful story. It shows how easy it is, even for a genius, to be led astray by, a gut feeling that turns out to be wrong.
We're committed to making these Nobel Prize-winning concepts clear and exciting, using vivid analogies.
You're talking bowling balls on trampolines.
Yeah. Rubber bands.
All the classics. So you can walk away with an intuitive grasp of ideas that confuse even seasoned physicists.
Because truly understanding gravity at this foundational level is essential for understanding the entire cosmos. It's the framework that defines everything from the behavior of light near a black hole to, the eventual fate of the universe.
If you can get your head around these three different ways of seeing gravity, you unlock a huge piece of cosmological knowledge.
Let's start with that first great revolution, the one that put Einstein on the map and fundamentally changed physics forever. He proposed that gravity isn't a force at all.
Not a force.
But a manifestation of geometry. And this whole idea pivots on a fundamental truth called the equivalence principle.
The equivalence principle is, it's the single most important concept in general relativity. It connects two seemingly distinct properties of mass.
Okay, so what are they?
First, you have gravitational mass. That's essentially how much oomph gravity exerts on you, how strongly it pulls you. Then you have inertial mass, which is how much oomph you need to exert to change an object's velocity.
How much it resists being pushed or accelerated.
Exactly. And what the principle states is that these two properties are universally linked. No matter what an object is made of, no matter how heavy it is, these two masses are numerically identical.
And that's not just a coincidence.
No. The universality of this link means that everything, regardless of its composition or mass, falls at the exact same rate in a gravitational field.
A fact first shown by Galileo, right? Dropping things off the Tower of Pisa.
Right. But Einstein saw the profound implication. He thought if gravitational effects and inertial effects are always the same, maybe they're actually two sides of the same coin.
Okay, to make this clear, we need the classic falling elevator thought experiment. It's the key to unlocking all of this.
It is. So imagine you are standing inside an elevator in deep space, millions of light years from any planet or star. You are totally weightless, just floating.
Got it.
Now, someone outside connects a massive rocket booster to your elevator and accelerates it upward at a constant rate, specifically at 9.8 meters per second squared.
Which is the exact acceleration we feel standing here on Earth.
The exact same. The moment that booster kicks in, you would feel yourself pressed against the floor. Yeah. Anything you dropped would fall to the floor with that same familiar acceleration.
And the brilliance of the equivalence principle is this. Inside that windowless box, there's no experiment you can do, nothing, to tell the difference between two scenarios.
You can't. Are you standing still on Earth, being pulled by gravity? Or are you accelerating upward in empty space? The experiences are absolutely perfectly indistinguishable,
That identity is what convinced Einstein that gravity wasn't a force.
but a property of acceleration itself.
Okay, let's flip it. The second part of the thought experiment. Free fall. Let's say you're in a spaceship orbiting Earth, like the ISS, or an elevator where the cable just snapped.
You feel weightless.
Right. Now, Newton would say that you and the elevator are both constantly being pulled by the Earth's huge gravitational force. You feel weightless only because everything around you
The floor, the wall.
is accelerating at the exact same rate toward Earth. So for Newton, your weightlessness is just an apparent illusion.
It's an illusion created by constantly falling together. But Einstein flips that script completely.
He says, wait a minute. If there's no experiment I can do to prove I'm being pulled by a force, maybe the sensation of weightlessness and free fall isn't apparent at all.
Maybe it's the true state of things.
Yeah.
Einstein suggests that in free fall, there is no gravitational force pulling you down.
So the force you thought you were feeling is what physicists call a fictitious force.
The fictitious force, exactly. It just arises because you're in an accelerating frame of reference.
Can you give me another example of that?
Sure. Think about being in a car that turns sharply to the left. You feel a push toward the right.
Yeah.
You get thrown against the door. But there isn't a genuine fundamental force pushing you out of the car. It's just your body's inertia. Your body wants to keep going in a straight line, but the car is accelerating underneath you. That feeling of being pushed is a fictitious force.
It's a consequence of motion, not an interaction.
And in Einstein's view, gravity in a localized free-falling frame behaves exactly like this.
So an astronaut in orbit, they're experiencing zero force.
Yes, that is the core GR insight. In free fall, your measured acceleration, what we call proper acceleration, is zero. You're feeling zero strain, zero compression.
So when I'm standing on the ground, I'm not in free fall.
Right. You're actually being pushed up by the floor. That's what creates that proper acceleration of 9.8 meters per second squared. That's why you feel heavy. The pull of gravity is only felt when something stops you from following your naturally straight path.
Okay, so if gravity isn't a force pulling objects, then what is causing the Earth to orbit the sun? Or an apple to hit the ground? If we eliminate the force, we need something else to guide the motion.
And that something else is the revolutionary idea. Curved spacetime. Mass doesn't pull, it warps. It changes the geometry of the stage where all the motion happens.
This is where we bring out the fast analogy. The universe as a huge, perfectly stretched, four-dimensional blanket.
We call it spacetime. It combines the three dimensions of space, up, down, left, right, forward, back, with the one crucial dimension of time.
Okay, so a massive object, like our sun, what does it do to the blanket?
It acts like a heavy bowling ball dropped onto that stretched sheet. It doesn't, reach out and pull things. It just causes the sheet to dramatically curve or warp around it. It creates this huge dip, this funnel.
So if you roll a small object, like a marble representing the Earth, across the sheet,
The marble isn't being pulled directly toward the bowling ball. Instead, the marble just encounters that curved surface and follows the straightest possible path it can find across that warped surface.
and because the surface itself is curved, that straightest possible path ends up looking like a circle.
It looks like an orbit to an outside observer. That straightest path is what Einstein called a geodesic. What looks like a pull is just an object moving in a straight line through a curved reality.
I love the other analogy of walking on Earth's surface. Let's say two people start on the equator, far apart, and they both start walking straight north.
Okay, they're both trying to maintain a perfectly straight line of travel.
But because the Earth is curved, it's a sphere, their paths will inevitably get closer and closer together until they meet at the North Pole.
And that convergence isn't caused by some mysterious force of attraction pulling them together. It's caused purely by the geometry of the spherical surface they're walking on.
The sun isn't pulling the Earth into orbit. The sun has just created a warp in the space-time geometry, and the Earth is simply moving as straight as it possibly can through that warp.
And this framework? It worked. It wasn't just a nice story. It solved real problems that Newton's gravity couldn't.
Like the orbit of Mercury.
Exactly. Mercury's orbit shifts, or precesses, a tiny bit over time. And Newton's equations were always off by a small but very measurable amount. Nobody could figure it out.
The General Relativity.
By modeling the sun as warping space-time, GR accounted for that extra curvature, and his predictions for Mercury's orbit matched the observations perfectly. That was one of the first huge successes that convinced people that geometry, not Newtonian force, was the right answer.
So the core insight is just so elegant. Matter tells space how to curve, and space tells matter how to move.
All is geometry.
But hold on, here's the critical question you raised earlier. If gravity is just fictitious, something you can get rid of by jumping into a falling elevator, how do we know the curvature is really there at all?
What's the ultimate proof that gravity isn't just an illusion we can ignore by falling?
Right. What's the smoking gun?
The smoking gun, the perspective-independent proof that space-time is curved, is tidal forces.
Okay, explain that.
This is the key physical distinction. The trick with the falling elevator thought experiment is that it only works perfectly if gravity is perfectly uniform everywhere inside the elevator. But real-world gravity, from a real object like Earth, is never perfectly uniform.
Why does it vary?
Well, gravity follows the inverse square law, right? It drops off with the square of the distance. So it's always slightly stronger nearer the object and slightly weaker farther away.
So for a person standing up, it's stronger at your feet than at your head.
Exactly. And the direction of the pull also changes. It's always pointing toward the center of the mass.
So let's go back to our incredibly tall falling elevator. If gravity was uniform, you'd float perfectly weightless. But because it's not.
Because Earth's gravity is stronger at your feet than at your head, you would actually feel a slight internal stretch, an elongation. Your feet are trying to accelerate toward the center of the Earth just a tiny bit faster than your head is.
And what about side to side?
Simultaneously, if the elevator is wide, the left side of your body and the right side are both being pulled toward the single point at the center of the Earth. So you'd feel a slight squeezing horizontally.
That stretching and squeezing effect, that's the tidal force.
That's the tidal force. And it's the true manifestation of the variation in the curvature of spacetime. It's the difference in the geodesics, those straightest paths, near a massive object.
And here's the profound part, right?
This is it. While the main force of gravity is fictitious, and you can eliminate it by choosing a free-falling frame, the tidal forces cannot be eliminated. They are intrinsic. They're real.
So even in free fall, you can never transform away the tidal effects.
Never. So the tides of our oceans, caused by the differential pull of the moon and the sun, those forces are the literal physical manifestation of space-time curvature. They are the actual real aspect of gravity that tells us, beyond a doubt, that we are living in a universe warped by mass.
And this is why astronauts in the space station, even though they look weightless, are not truly weightless.
Exactly. They're still subject to small, measurable tidal forces. Those forces confirm the persistence of curvature. If gravity were a simple Newtonian force, it would all be eliminated in freefall. Because tidal forces remain, general relativity stands confirmed.
Okay, we've established that gravity isn't a simple force, but the curvature of space-time. That's revolutionary enough for one deep dive.
You'd think so.
But physics never rests. And now we move to a modern idea so radical it makes Einstein's geometry look, well, conventional. The idea that gravity might be a statistical phenomenon.
Arising from information and heat.
This is truly physics on the bleeding edge. It's called entropic gravity.
Or sometimes emergent gravity. Its primary champion is the Dutch theoretical physicist Erik Verlinde. And this theory suggests that gravity is not a fundamental interaction, not an innate, irreducible property of the universe like electromagnetism.
But an emergent phenomenon. I need a better definition of emergent here. What does it mean for gravity to emerge?
Okay, think about the properties of water. Wetness, liquidity, flow. These are macroscopic properties that emerge from the collective behavior of trillions of individual H0 molecules interacting in a certain way.
Right. A single H2O molecule isn't wet.
Exactly. Wetness is an emergent property of the group. Entropic gravity suggests that gravity, as we experience it, emerges from the collective statistical behavior of something far more fundamental, microscopic bits of information.
So the pull of gravity is actually an effective macroscopic force driven by the statistical tendency of a system to increase disorder. This sounds like the rubber band analogy we talked about.
That's the best way to grasp an entropic force. Take a rubber band and stretch it out. It snaps back. We feel that snap back as a force.
But at the molecular level, there's no fundamental spring force pulling the polymer chains back together. It's not like there are tiny little springs in there.
Not at all. The sources explain that the relaxed, coiled state of the rubber band has vastly more high entropy or disordered configurations than the stretched, ordered state.
There are just more ways for it to be messy than for it to be neat.
Millions more ways. The rubber band snaps back because of a statistical overwhelming tendency to maximize the number of ways its molecules can be arranged, to increase disorder, to increase entropy. The force is just the macroscopic reflection of the universe's preference for chaos.
And entropic gravity suggests the pull of the Earth is the same thing?
On a cosmic scale, yes, it's statistics and disorder.
That is a massive conceptual jump. How did physicists even start to connect gravity to concepts like information and heat?
It all started with black holes in the 1970s. The physicists Jacob Bekenstein and Stephen Hawking showed that black holes have measurable entropy, they have disorder, and they have a temperature.
Which was a shocking discovery.
It fundamentally linked gravity, which defines black holes, and thermodynamics, heat, temperature, and entropy.
So this theory is built on black hole physics.
Absolutely. It uses a concept called the holographic principle. This radical idea suggests that all the information needed to fully describe everything inside a volume of space, say, this room, can actually be encoded entirely on its two-dimensional boundary surface.
It's like a gigantic 3D hologram projected from a flat plate. So our perception of three-dimensional space and the gravity within it might just be a projection.
That's the wild implication. Verlinde proposes that this boundary surface, this holographic screen, is covered in tiny fundamental bits of binary information, like pixels on a cosmic monitor. And the total number of these bits is proportional to the area of the screen.
Okay, so you have a screen of information bits. How does mass come into play?
We use Einstein's most famous equation, B is CUA. Mass and energy are equivalent. The theory postulates that the energy contained within a mass is distributed evenly over those microscopic information bits on the holographic screen.
And when you spread energy over lots of little bits,
The system gets a quantifiable temperature, just like the molecules in a gas. The higher the energy density on the screen, the higher the temperature of the screen.
so mass literally generates heat on the boundary of space itself.
In this model, yes. Now, here's the key part. When a small particle with mass m approaches this screen, it changes the total amount of information needed to describe the space. It causes a change in entropy.
It messes up the information on the screen.
It puts the system out of equilibrium, and the universe, just like the rubber band, wants to maximize its disorder and restore that balance.
And the force we feel as gravity is just that statistical pushback toward equilibrium.
Yes. Verlinde combined the definition of an entropic force, this idea that force is related to temperature and the change in entropy, with these holographic principles. And by doing the math, by substituting in the temperature and entropy from the information bits,
He derived Newton's law of gravitation. F equals gmm over r squared.
he derived it practically from first principles, from information theory and thermodynamics, not from geometry or a fundamental pull. It suggests gravity is simply an entropic force pointing in the direction of increasing disorder.
It suggests that when I drop an apple, it's not accelerating toward Earth because of a pull or a curve.
It's accelerating toward a state of maximum statistical entropy. It is the universe statistically trying to restore equilibrium.
Wow. Now, one of the biggest reasons entropic gravity gets so much attention and so much controversy is its potential to solve the biggest puzzle in cosmology,
Dark matter.
the dark matter problem.
The dark matter problem is huge. Mainstream physics uses this idea of dark matter, some unobserved, unseen, massive entity, to explain why the outer edges of galaxies spin way too fast.
Based on the visible matter, the stars should just fly off into space. There isn't enough gravitational glue.
Right, so we invented this invisible glue called dark matter.
But entropic gravity offers an alternative explanation.
Yes. It argues that the missing gravitational effects are not caused by invisible particles, but are the product of quantum effects that inherently exist in the vacuum of space. The missing gravity is a structural quantum effect arising from the information structure of the cosmos, not from unseen mass.
That would be a huge relief, getting rid of a particle we've been searching for decades. The sources also mentioned that this theory connects strongly to another controversial idea, right? MOND.
MOND. It stands for Modified Newtonian Dynamics. It's an older theory that just says, hey, maybe when gravity becomes incredibly weak, like at the vast distances between galaxies, Newton's inverse square law of gravity breaks down.
So instead of getting weaker by the square of the distance,
MOND suggests it decays linearly with distance. So the pull is stronger than Newton predicts at those very large scales.
and entropic gravity predicts this.
It's inherently consistent with it. Verlinde's theory predicts that once gravity becomes vanishingly weak, the classic inverse square nature transitions into a linear decay. It provides a theoretical mechanism for MOND-like behavior, which is crucial because MOND, as a model, is incredibly good at predicting galactic rotation curves.
This sounds incredibly compelling. It solves dark matter and provides a foundation for MOND. But it's still highly debated. So where does the controversy lie?
The community is sharply divided. For one, it's just really hard to test. But on one hand, you have studies analyzing the gravitational fields around tens of thousands of galaxies that show results consistent with Verlin's theory.
But on the other hand, the evidence for dark matter is very strong in other areas, isn't it?
Yes. For example, large-scale observations of gravitational lensing around galaxy clusters, how massive objects bend light, often seem to contradict entropic gravity unless you add dark matter back into the equations, which sort of defeats the purpose.
So it works for galaxies, but maybe not for galaxy clusters.
It seems that way. And there are deeper theoretical problems. Critics argue that trying to model forces using entropy and temperature for multiple masses requires unphysical requirements, like you need many separate temperature baths in the universe, which just seems unnatural.
And there's a conflict with quantum mechanics.
A big one. Entropic processes, by their nature, tend to destroy order and break what's called quantum coherence, the ability of quantum states to stay linked and predictable. If gravity is truly entropic, we should see evidence of this coherence breaking.
But we don't.
Experiments with ultra-cold neutrons have looked for it and haven't found it. The microscopic reality just doesn't seem to line up with the entropic force description.
So we have a profound dilemma. We have general relativity describing gravity as geometry, working perfectly for black holes and planets. And we have entropic gravity describing gravity as information and heat, which works elegantly for galaxies without dark matter.
They both seem useful, but they offer radically different views of the universe. And the challenge is, their predictions only really diverge in extremely weak gravitational fields, making a decisive test incredibly hard. It's an ongoing revolution.
We've talked about Einstein's ultimate success-replacing force with geometry, and how radical modern theory is trying to replace geometry with statistics. But what often gets lost is the human side of the story.
The struggle.
The incredible intellectual struggle Einstein endured between 1912 and 1915.
It's one of the great stories of modern science. Einstein had the brilliant physical insight: gravity and acceleration are equivalent, so spacetime must be curved. But going from that idea to the final, correct mathematical law took 3 years of frustrating dead ends, self-doubt, and some major blunders.
It shows that finding the language of the universe, the perfect equation, is often harder than having the big idea.
Absolutely. His path started to get clear around 1911 and 1912. He realized the equivalence principle had these massive, tangible consequences.
First, he realized gravity had to affect light.
Right. If acceleration bends light, and acceleration is equivalent to gravity, then gravity must bend light. His early calculations showed that the velocity of light is slower in a stronger gravitational field. He also stated that since mass and energy are equivalent, all energy must create a gravitational field.
And then came the insight about time.
By 1912, he had reached the critical insight that gravity bends time. He figured out that a clock in a higher gravitational potential, farther from a mass, runs slightly slower than one closer to the mass.
That's gravitational time dilation. And it's real. We have to account for it in our GPS satellites or they wouldn't work.
Exactly. So by 1912, he had the physical principles. Gravity is geometry, it bends light, it warps time. But he needed the math. He needed the equations to describe how matter dictated this curvature.
This is where he went to his friend, the mathematician Marcel Grossmann.
Yes, Einstein was looking for generally covariant field equations, equations that work no matter how you measured or described the system. Grossmann introduced him to the complex tools he needed: tensor calculus and Riemannian geometry.
And this is where the incredible stumble happened.
It's astonishing. Einstein actually considered the correct final field equations, the ones involving what's called the Ricci tensor, around 3 years before he finally published them. We can see them in his notes.
In his Zurich notebook, he had the right answer staring him in the face.
And he threw it out.
Why? What was the mistake?
He fell into a trap of his own physical intuition. We call it the flat space trap. He believed that in a weak field approximation like the static gravity we experience every day, the spatial part of the field should be simple, or flat. He just assumed that space itself should be uncurved, even with gravity present.
That seems like a reasonable assumption based on Newtonian physics.
It was a reasonable assumption, but it was mathematically incompatible with the generally covariant equations he had derived. He needed his grand new theory to reproduce Newton's theory in simple cases. That's the Newtonian limit.
And the correct equations seem to fail that test.
They failed the test if he forced his flat space assumption on them. So he convinced himself the mathematically correct equations were physically wrong.
So his gut feeling, his intuition from the old physics, led him down the completely wrong path.
Exactly. For 3 years. The consequence was a huge intellectual detour. From 1912 to 1915, he abandoned the principle of general covariance and focused on finding limited equations instead, the Entwerf equations. It was a massive concession. He was settling for equations that only worked under certain conditions.
He must have been deeply frustrated.
Oh, he was. The sources, his letters, they show he was constantly battling self-doubt. He wrote to Hendrik Lorentz in 1913 saying his confidence in the theory was still shaky. He knew the equations felt incomplete, but that flawed intuition about the flat space limit kept him stuck.
It's amazing to think that while he was struggling, other physicists were also racing to solve the same problem.
Absolutely. By late 1915, he realized his Entwerf equations were fundamentally flawed. He wrote letters admitting he was in despair and had to start over. And this was a high-stakes moment because David Hilbert, another brilliant mathematician, was working furiously on the same problem. The pressure was immense.
So what finally caused the breakthrough?
He realized his original assumption, the flat space trap, was just wrong. He realized that static space does need to be curved, even in the weak field limit, and that this curvature was actually required to maintain the Newtonian limit correctly.
Once he let go of that bad assumption.
He can return to the demand for general covariance. And the correct equations, the ones he had thrown out in 1912, they just clicked back into place.
And in a dramatic series of papers in November 1915, he finally published the complete and final form of the equations of general relativity.
Yes, he even admitted in a paper that he had completely lost trust in his previous equations and had returned to the demand for general covariance, from which he had parted, though with a heavy heart, 3 years ago.
His struggle highlights such a profound lesson. The human mind can sometimes reject truth because it conflicts with what we expect to see. The math is often the true guide.
And even a genius can be trapped by flawed assumptions. But what came out of it, general relativity, is still the framework for all current work in gravitation.
Wow, what an incredible journey. We moved from Newton's simple idea of gravity as a mysterious pull
Action at a distance.
to Einstein's revolutionary idea of gravity as curved geometry, where objects simply follow the straightest path across warped spacetime.
And then we leaped into the 21st century with the idea that gravity might not even be geometry, but an emergent statistical phenomenon. In this view, gravity is the echo of information and heat trying to find balance.
The key takeaway for you, the listener, is just how profoundly different these models are, force, geometry, or statistics, and yet they all successfully describe aspects of the reality we observe. Gravity is absolutely not simple.
Right. And the fact that 3 distinct models, Newtonian, general relativity, and entropic gravity, can all be useful, proves George Box's famous quote, "All models are wrong, but some models are useful."
Newtonian works for throwing a baseball, GR works for black holes, and maybe entropic gravity works for galaxies.
They work within specific limits, showing us that our understanding of the universe is still just a collection of successful approximations.
That brings us to our final provocative thought. General relativity fundamentally tied gravity and spacetime together. You can't have one without the other.
They're inseparable.
So, if gravity is truly emergent, as entropic gravity suggests, then spacetime geometry must also be emergent.
That's the logical conclusion. If the pull of a planet is just entropy, if every time you feel yourself grounded, you're experiencing the universe's statistical tendency to maximize disorder, then gravity is fundamentally heat and information.
So the question then becomes,
If the fabric of reality, space, and time itself is merely an emergent property, what is the true, non-spatial, non-temporal fundamental code that is generating that information in the first place? What is the reality beneath the illusion?
that is a cosmic mystery to chew on. Thanks for coming along on this deep dive with us. Remember to follow us on your favorite podcast platform and see you on the next dive.